Hello, I'm Christian Homeyer from the University of Heidelberg and here to present our work on moving object segmentation from monocular video with transformers. This research has been conducted while working in Bosch Research Germany. We live in a dynamic world where it is necessary to accurately detect and segment other autonomous agents. While humans can effortlessly perceive even completely unknown objects, this task can be very challenging for monocular video alone for modern systems. Moving object detection and segmentation can be considered a binary instance segmentation problem, where we are given a video and want to segment a single frame. Generic detection means the test set may contain potential object classes that are not in the training data. Finally, non-rigid motion often results in multiple patterns. We define a moving object as their aggregation. For example, when a person moves only an arm, the whole person should be segmented. We could use the video stream directly to solve this. However, this turns out to be very challenging, especially when seeing unknown objects. Similar to the two-stream hypothesis in neuroscience, which states that humans use both recognition and motion in two different streams to process incoming data. We use both knowledge of reconstruction and recognition to make the task easier. We therefore create additional what we call pseudo-modalities like optical flow or 3D scene flow. Note how moving objects get much more easily revealed in a motion map like optical flow. This leads to a multimodal fusion problem, where we combine motion and appearance features for a robust segmentation. Motion segmentation has been a long-standing problem in computer vision, with many papers up to date. Previous work either only considers single modalities, most prominently optical flow, or in a combination of image data and optical flow. Other papers rely on handcrafted 3D geometric criteria. Usually data is combined in a fixed way using a convolutional neural network. In our experiment design, we systematically compare different motion representations from 2D to 3D and use a transformer architecture. Finally, previous work all use different datasets for training, which makes the comparison hard to undertake. It is important to note that datasets also differ widely in terms of motion diversity, semantic classes, and degenerate cases. In our work, we keep things simple. We compute either 2D optical flow or 3D scene flow as a motion representation. In order to compute scene flow, we first infer single image depth maps for multiple frames of the video. We then input both appearance and motion into a state-of-the-art transformer architecture for segmentation. Extending a transformer architecture to multiple modalities is straightforward. We simply concatenate the tokens to a longer sequence and adapt the positional encoding. We use a two-stream architecture where we have two separate training weights for motion and appearance. As is common, we freeze the appearance branch after pre-training on COCO to preserve general object appearance knowledge. Both streams can then exchange information via the attention mechanism. We base our model on the recent state-of-the-art MAS2-form architecture. It is an encoder-decoder architecture. Since we extended it to multiple modalities, we call our framework multimodal MAS2-former, or in short, MCube-former. Since it is a query-based detector, we have a fixed set, for example, 100 object queries. Since we have an appearance and motion stream, we have two sets of features and two sets of queries. Features are combined with the attention mechanism on multiple scales of the feature pyramid and exchange information with both sets of queries. Now, multimodal models can suffer from an alignment problem. When encountering multiple sources of information, the network needs to decide which one to trust more or how to align them successfully. Models can quickly learn to only segment classes that can potentially move. In addition, common datasets often lack diverse scenes where normally moving objects remain static. Instead, objects move all the time. We propose a simple fix for this problem. We introduce negative examples where the motion map does not contain any variation, thereby forcing the network to always consider the motion map when determining the final class label. In our first experiments, we analyzed the effect of the motion representation for segmentation performance. We simply train a MAS2-former model with pure motion data as input and train on the common scene flow datasets as previous work. We noticed that while 2D optical flow is a representation that can be robustly computed in most datasets, it cannot help in degenerate motion cases often encountered in autonomous driving. 3D scene flow gives a unique and minimal representation to resolve these cases, but it depends largely on the quality of the computed depth maps and is therefore noisy. Higher dimensional handcrafted motion costs from previous work seemingly offer a middle ground here. However, finally, segmentation from performance purely based on motion cannot achieve the same precision as a simple image detector baseline, which was often overlooked in previous work. The reasons for this are multiple-fold. First, degenerate cases and faulty motion maps can lead to many false positives. Second, Non-rigid motion patterns need to be grouped together into whole objects in order to achieve good performance. Moreover, in common driving scenarios, we encounter multiple objects moving collinear with the same motion pattern. This leads to an under-segmentation of the scene. If such cases have never or rarely appeared in the training data, then models will logically not be able to do this. In order to resolve these problems, we combine both modalities and train on more diverse training datasets. Using multiple modalities can improve single modalities and a pure image baseline. However, we notice that by using only the scene flow datasets, we cannot beat the state of the art. We realize in our experiments that this is due to a lack of data and the aforementioned reasons. Only when using more diverse training data can we achieve state-of-the-art performance. We notice that our models behave logically. If non-rigid motion patterns are not present in the training data, then the model will not be able to group them. Note how our models still have never seen the test data. Remarkably, even though Mix 2 does not contain any real driving data, we can achieve strong performance on Kitty while only using appearance and optical flow. While scene flow seems to be the better representation when high-quality depth is available, a robust representation like optical flow works better on in-the-wild datasets like Davis. While appearance data is clearly the main driver for detection and segmentation, motion data classifies an object into moving or static. However, there are also scenarios where motion can be a strong cue for an object. Training our transformer model robustly on diverse data makes them more robust to also out-of-distribution data like camouflaged animals. Interestingly, in our two-stream architecture, we can observe that the attention and gradients are focused much more locally in the appearance stream, while being more global in the motion stream for classification. We could improve results in a straightforward manner. However, our final models still exhibit multiple failure cases. These failure cases are likely due to data and not architecture. With this, I'll conclude my talk. Thank you for your attention.